So here we got a nice algebraic problem that appeared in 2006 IMO. So problem state that P be a polynomial of degree n greater than 1 with the integer coefficients. So we are given a polynomial P of x which has a degree n which is greater than 1 and P belongs to Z. And let K be a positive integer, so K is our positive integers, and we are given another polynomial Q of x which is defined as P raised to the power k x. So we have to simply prove that there is at most an integer solution of the equation Q of t equals t. So I'm going to use a lemma that is very helpful. If we know that P raised to the power x equals x, then it simply implies that P raised to the power 2x equals x. And another lemma is that if a and b are two distinct integers, then it simply implies that a minus b divides p of a minus p of b, where p is a integer polynomial. So let's start solving the problem, and I'm going to assume let Q of t equals t has at least n plus 1 integer solutions. So this is the contrary assumption. So here we can make two conditions. The first one is that for every x which is the solution of Q of t equals t simply satisfies that P of x equals x. But this simply implies that the number of integer solution is at most n, because we know that polynomial P has degree n, so the number of integer solution can be at most n. But our assumption is there is at least n plus 1 solution, so it simply implies the second condition that there must exist some y which is the solution of Q of t equals t but does not satisfy P of x equal x. So here one thing we have to consider, that by our above lemma P raised to the power x equals x implies that P raised to the power 2 x equals x. You can say that this satisfies the equation P raised to the power 2 x equals x by first lemma. Fine. And now we can use our second lemma, which is a minus b divides p of a minus p of b. So we can say that x minus y divides p of x minus p of y, and this simply divides p applied to px minus p applied to py, and we know that this is our equal to x and this is equal to y. So we can use our divisibility criteria, which is if a divides b, then it simply implies mod of a is smaller than or equal mod of b. So we can say mod of x minus y is smaller than or equal mod of p of x minus p of y. This is smaller than or equal to mod of x minus y. So since the edges are same, we can simply say that mod of x minus y equal mod p of x minus p of y. We can simply solve this in two ways. The first is x minus y equals p of x minus p of y, and we know that p of x equals x, so we can simply cancel these two and we'll obtain y equals p of y. And the second way to solve this, x minus y equals minus of p of x plus p of y. So we can simply say that x plus p of x equals y plus p of y. This is the second result that we obtain. So we already have assumed in our second condition that the y does not satisfy this condition, that p of x equals x. So this first result is false. This is not going to be happen, and we are only left with this second result, which is x plus p of x equals y plus p of y. And we know that we started from p raised to the power x equal x, and this result simply implies that p raised to the power 2x equals x. And by using this equation we have obtained x plus p of x equals y plus p of y. So we can simply say that p raised to the power k x equal x implies x plus p of x equals y plus p of y, where y is a constant. So we can simply rewrite this equation as x plus p of x equals c, some constant, and it has at most n solutions, n integer solutions. Since we know that polynomial p has a degree n, so this expression must have at most n integer solutions. And now we can simply say that our equation q of x equal x also has at most n integer solution.